Hello, in this video I'd like to talk about weak S1S, or the weak monadic second-order theory of one successor. So what does it mean to study a theory with one successor in it? Well, when I talk about successors, I'm talking about exactly the same thing that we were talking about in the last video. This idea of having words and tacking an A or a B onto the end of them. But of course, if we only have one successor operation, we really only have one letter in our alphabet, this winds up corresponding to just talking about the natural numbers. So for instance, we say that the word A represents the number 3. The successor A operation corresponds to the +1 operation, which we're actually going to denote in this video as just S with no subscript as a unary function. In accordance with our analogy, the empty word corresponds to the number 0, and this word here is just successor A of successor A of successor A of the empty word, which corresponds to the successor of the successor of the successor of 0. So really, when we're talking about a theory with one successor, we're really just talking about the natural numbers with a successor operation to them. When we talk about a theory, that means that we're really interested in the set of true sentences for this particular structure in the language that we're going to define. Recall that second order means we're interested in talking about not just natural numbers, but also maybe sets of natural numbers or functions or relations on natural numbers. When we see the word monadic, this restricts what sort of second-order objects we're interested in studying. In particular, this means that we're going to restrict our attention to just sets of natural numbers. Another way to think about this is that we're restricting our attention just to unary predicates on the natural numbers, but unary predicates are really the same thing as sets of natural numbers, right? A unary predicate is true of some natural numbers and false of other natural numbers, and so you can consider it to correspond to the set of natural numbers for which it is true. So we're exclusively interested in studying sets of natural numbers. And then this weak here tells us that we're actually only interested in finite sets of natural numbers. So I'm actually going to describe this structure that we're interested in studying as having two different types. One type which corresponds to natural numbers, and another type which corresponds to finite sets of natural numbers. And just how you have a calligraphic P that represents the power set of the natural numbers, the set of all subsets of the natural numbers, I'm going to want to use an F to represent the set of finite subsets of the natural numbers. So here we have a structure with two types, the natural numbers and also finite sets of natural numbers. We have our successor operation because that's what we specified that we have. This is an operation that takes in a natural number and outputs a natural number, specifically that number +1. And then we have containment. If we have a natural number and we have a finite set of natural numbers, we want to be able to talk about whether that natural number is in that finite set of natural numbers or not. And this is it. This is an extremely simple structure that nonetheless winds up being expressively equivalent to the regular languages. So personally, I like to think of the language that we're going to be looking at as the first order theory of this two-typed structure, because that's exactly what it is. It's exactly how you would construct the first order theory of any other two-typed structure. It just happens to be the case that one of the types is sets of the other type. This term second order here comes with a lot of baggage, and it comes with the implication that we're doing something really powerful that involves set theory. But it turns out that the theory of this structure, being expressively equivalent to the regular languages, doesn't have the same sort of concerns as you would have with most second order theories, where you're really concerned about a lot of set theoretic things. One of the things that I really like about this name is that it naturally suggests a couple of directions of generalization. For instance, we could drop the weak requirement and say that we're interested in studying all sets as our second order object. We can also change the one. What happens if we're actually interested in having two different types of successor, a successor A and a successor B? Then the objects of our structure go back to being, instead of natural numbers, words on the letters A and B. As one might anticipate, we don't actually gain very much by going from 2 to 3 letters or any other finite number of letters, but we can also ask what happens if we have infinitely many letters, and then something slightly interesting happens in that case as well. These sorts of structures have been well studied and wind up having their own theories that wind up being very similar to what we've talked about here. They wind up having a notion of deterministic and non-deterministic automaton. They wind up having a notion of regular expression. They even wind up having their own Myhill-Nerode theorems. You can look forward to a future series of videos where I go through all of these generalizations. But for now, we're just going to want to focus on the weak S1S, which is equivalent to the regular languages, which is what we're talking about. So this structure actually has two types of terms. It has terms that represent natural numbers, and it has terms representing sets of natural numbers, objects of the second kind. And we actually don't have a lot of built-in terms. We have, of course, variables, which are all going to be lowercase if they represent natural numbers, and going to be uppercase if they represent sets of natural numbers. And because we have a unary function on the natural number terms, we also have a built-in, if we have a term representing natural numbers, then the successor of that term is also going to represent a natural number. And this is it. These are all the built-in terms for our structure. There's not a lot of them. But we can also talk about things like 0, for instance. This is going to be just like the empty word could have been in our previous video. It's going to be notational shorthand, right? We don't actually need a constant symbol representing the number 0, because anytime you had a formula saying something about the number 0, you could turn it into a formula saying something about the number x, and then saying that x met the properties that the number 0 does, specifically that it's not the successor of anything. And then, of course, once we have the ability to talk about 0 in shorthand, we also have the ability to talk about the successor of 0 and the successor of the successor of 0, and so on and so forth. And for shorthand, I'll use 1 and 2 and 3 and so on and so forth to represent these particular terms. And then, once we have the ability to talk about these specific natural numbers in our shorthand, that also gives us the ability to talk about specific finite sets of natural numbers, describing as shorthand for these second order terms. So for instance, if I wanted to describe the set 0, 1, 3, again, that's shorthand. We don't have to assume that it's part of our language, but this set here, anywhere that we had a formula including this set, we could simply replace it with a capital X and then specify that for all elements within capital X, that element is either equal to 0 or 1 or 3, and 0, 1, and 3 are actually in that set. So again, we have notational shorthands that allow us to talk about all of these things without having to worry about them actually being in the base of our language. From these terms, we can then construct our atomic formulas. Again, we're going to want to toss in equality for free, just because that's the model theoretic thing to do. So we're going to want to be able to, and we're actually going to want to have two types of equality. We're going to want to be able to say that a first order term is equal to a first order term, But we're also going to want to be able to say that a particular second order term is equal to a particular second order term. And then finally, we're going to want to be able to say that a particular first order term represents an element of the set represented by a particular second order term. So these are all of the things that our atomic formulas could be, where I'm using lowercase t's to represent first order terms and uppercase t's to represent second order terms. From this base, we then recursively construct the set of all formulas. Again, we're going to want our Boolean connectives. So if we have a formula, then not f is a formula, f and e is a formula, f or e is a formula, f implies e, f if and only if e, things like that. We're going to want to toss those in as well. And then also quantifiers. And again, because we have two different types of variables, we're going to have two different types of quantifiers. We're going to be able to say both for all first order objects, some formula, hopefully involving that variable, is true. But we're also going to be able to say for all second order objects, x, some formula is true about them as well. And of course, there exists a first order object making a particular formula true, and there exists a second order object making a particular formula true. And again, this is how you would recursively define the first order theory of a two-typed structure, right? You would have quantifiers for both of those types. You'd have different types of variables for both of the types, and you'd have equality of the two different types. And so in my mind, the only reason why we're calling this a second order theory is the fact that this type here represents sets of the first type. So what sorts of things can we actually say with this language? There doesn't seem to be that much going on, so what can we actually do? Well, we can talk about less than or equal to. In particular, we need to start by defining the notion of a downwards closed set. So I say that a particular set is downwards closed if, for every natural number, the successor of that number being in the set implies that that number is in the set. Right? The idea is that we want this set, remember that this is a finite set of natural numbers, so we want this set to be all of the numbers from 0 up to a particular number. And again, we can recognize that by talking about what it means for the set to be downwards closed. And then once we have this notion, we can determine if a particular number is less than another number if every set that is downwards closed and contains y also contains x. Interestingly enough, we can define successor in terms of less than or equal to, and so we could actually swap the places of successor and less than or equal to, where less than or equal to is something fundamental to the structure, and then successor is just shorthand for a formula involving less than or equal to. And so you could say, instead of studying the weak monadic second order theory of one successor, that we were actually studying the weak monadic second order theory of a particular type of linear ordering. These two are effectively the same. It's worth noting, however, that we can't talk about plus or times. And I'll explain why in a future video. It's a little bit tricky. It's easy to show that you can talk about something. You just write out the formula and you say, here's what we could do if we wanted to talk about some number being less than or equal to some other number. But if we want to say that we can't talk about something, that's going to be a little bit trickier to prove, that there can't be a formula that does a particular thing. So we'll save this for a future video. We can, however, talk about the even numbers. We can say that a particular number is even if for any set that contains our particular number and whenever the successor of the successor of y is in that set, then y is in that set. So that's similar to being downwards closed, but not quite the same. It's closed under going down 2 steps. So if we have a set that contains n and is downwards closed by 2 steps, then that set necessarily contains 0. We can talk about, because we can talk about less than or equal to, we can talk about the minimum or maximum element of any particular set. Remember that because these sets are finite, we're talking about the weak second order theory. All of these sets here are finite, so they're all going to have a maximum element. And again, we can talk about those in this logic. And we can talk about a bunch of set operations. We can talk about the union of 2 sets, we can talk about the intersection of 2 sets, and we can talk about the difference between 2 sets, all of the elements that are in one but not in the other. So this is a surprisingly robust language, even though there aren't that many pieces to it. And in fact, as I mentioned before, it winds up being expressively equivalent to the regular languages. So anything you can do with an automaton, you can do in this particular language. But we need to do a bit of a translation in order to even be able to make sense of that statement. So just as before, we can turn any formula into a corresponding finite state automaton. So given a formula with free variables of the first type, x1 through xn, and free variables of the second type, y1 through ym, in our particular logic, there's going to be a corresponding finite state automaton, a sub phi, which accepts the tupling of representations of particular first order elements and particular second order elements. We need to figure out how to take first order and second order elements and represent them as words, and then we need to tuple those words together, and we're going to feed that tuple into this particular automaton, and this particular automaton is going to accept if and only if phi actually holds when we take these particular first order elements and plug them in for the x's, and when we take these particular second order elements and plug them in for the y's. And we're going to want to say that a sub phi rejects if it's fed invalid inputs. So how can we represent first order elements and second order elements as words? Well, we have a few choices here, but I like representing number n as a to the n followed by b, right? So a word with n a's followed by a b. And then we can represent a set of natural numbers. This is going to be the shortest word with b's at positions indexed by elements of n. Right, so the positions in the word will start counting at 0. The positions in the word will correspond to various different natural numbers. We'll put b's at all of the positions that correspond to elements of x. And then we'll put a's everywhere else up to the position of the furthest b. So for instance, suppose that our formula, phi, it just has 2 free variables, x and y, and the formula is just x is in y. So a super simple formula, and by this theorem we can convert it into an automaton, and that automaton, well, because it's the case that phi of 0, the set 0, 1, 3, we're going to want it to be the case that a sub phi accepts this particular tuple here, right? What we're trying to do is we're trying to say that 0 is in the set 0, 1, 3, and so we're going to feed into our automaton a representation of 0. So this is 0 a's followed by a b for this first word, and then a representation of our set in positions 0, 1, and 3, we're going to put a B. We'll fill the rest in with A's up to the furthest length. So this here is how we represent these inputs as something we can feed into our automaton. And then we're going to want it to be the case that because this formula is true of these inputs, our automaton is going to accept this representation of those inputs. On the other hand, the fact that it's not true that phi holds of 4, 0, 1, 3 is going to correspond to the fact that A sub phi does not accept the input. So how do we represent the input 4? Well, we're going to have 4 A's followed by a B, and then we represent this set the same way. So that gives us the two words that we're going to want to tuple together. In order to tuple these words together, we need to pad them so they're the same length. And then we take the first characters, the second characters, the third characters, the fourth characters, and the fifth characters. And that gives us the word that we're going to want to feed in to A sub phi. And the automaton is going to reject this input because we've built it to only accept things where this winds up being true. So I'll let you take a moment to figure out how we can build an automaton that does this particular task, because it's going to be super important as part of the base case of our proof. And we're going to want it to be the case that if we feed in a bad representation into A phi, if we feed in something that couldn't be a translation of inputs of the appropriate types, we're going to want it to reject. But it's actually not that bad to build an automaton to check to make sure that all of the inputs are of appropriate types, and then just kind of like add that in as a piece to any automaton that you want to build to do any other task. So the proof of this fact is almost identical to the proof in the video about the word logic. Our first step is going to be to relationalize our structure. We have this successor operation, and we're going to want to take all of our formulas and break them apart if they involve a successor, so that all of the atomic formulas within them look like S of x is equal to y, right? We don't have successor of something, and we're not saying things like, I don't know, the successor of x is in a particular set. We take those formulas, we break them apart so that we're doing the successor bit in one atomic formula, and we do the containment bit or other successor bits in other atomic formulas. Next, we prove our assertion by induction on the construction of the formulas. We first prove the base case with all of our basic atomic formulas. Remember that there's actually two types of equality, so there's an extra atomic formula that we need to be worried about. And then the inductive step is just how we combine formulas to produce larger formulas. So the Boolean operations, straightforward. Again, we appeal to the closure properties video. We need to be a little bit careful when it comes to existential quantifiers, but if we require our automata that we're constructing to only accept valid inputs, that pretty much takes care of everything that we could worry about. And of course, universal quantifiers have to be broken down into saying that there isn't a counterexample. And then we use the fact that we've done the proof for not and there exists in order to show that it inducts through universal formulas. So I encourage you, if you're interested, to work out the details of this proof for yourself. But I don't want to waste your time if you're not interested in those, because again, it's almost identical to what we did previously. And we also have the reverse. So previously we converted formulas into automata, which showed that the formulas are no more expressive than the regular languages. But what if we have an automaton? What if we have a regular language? How can we convert that into a corresponding formula? Well, again, we're going to want a translation technique. We're going to want a way of turning a word into a collection of first or second order objects. So to put this formally, for every regular language L, which is a subset of sigma star, sigma can be any finite alphabet here. It's very easy to generalize this to however many letters you want. we can find a formula phi in weak S1S such that W is in L, that is W, a word, is accepted by the corresponding finite state automaton if and only if phi holds of an encoding of W. So what is this encoding? How do we encode words in terms of the objects of weak S1S? Well, we're going to encode a word by actually two second-order objects, assuming we have two letters. We're going to have x sub a, and we're going to have x sub b. And this is going to be the set of all positions where in W, where we have an a, and this is going to be the set of all positions in W, where we have a b. And if we have other letters in our alphabet, we just add extra second-order objects. So for instance, if L is our odd number of A's, no C's language, then the fact that the word AA, BAB is in L, we can take L and we can translate it into a corresponding formula. This formula is going to take in three inputs. It's going to take in an XA, an XB, and an XC because there's three letters of this alphabet. So this formula here, in order to translate this word into something that we can feed into the formula, we're going to want to look at the indices where each of these letters occur. So the indices where the A's occur are 0, 1, and 3. The indices where the B's occur are 2 and 4. And the indices where the C's occur are, well, that's the empty set. And so here we have these three objects of the second type in weak S1S. We're going to plug them into the formula that we get from this theorem, and it's going to wind up being true because the corresponding word is in the language. And essentially, the formula that we're going to wind up constructing is just going to say the first entry is going to be set with an odd number of elements, right? An odd number of A's, an odd number of positions where A shows up. The second set, there's going to be no requirements on that yet. And then the third set is going to be empty because there are no C's, no positions where C shows up. And then, of course, we're going to require all of these formulas to only be true if this is a valid input, if this is a valid representation of a word. So in particular, in order to be a valid representation of a word, these sets have to be a partition of the numbers from 0 to n for some n. But again, we can construct a formula that describes when that happens. That's not a big deal. And again, the proof of this fact is almost completely identical to the proof in the video about the word logic. So I'll actually let you try to adapt that proof to weak S1S. All you have to do is take the formulas and instead of expressing these things in the word logic, try to express them in weak S1S. So this here, weak S1S, is the logic that people will think about when you say, oh, I'm studying a logic that corresponds to the regular languages. This is the one. This is the big one. But as we've seen, there are other logics. There's the word logic, and in the next video, I'll talk about yet another logic called Buki arithmetic that also winds up being equivalent to the regular languages with almost exactly the same proofs. So let me know in the comments if you have any questions, particularly if you got stuck somewhere in doing these constructions for yourself, and I hope to see you then.